I am Nicolas Chieni with Siemens PLM software. Today, I'm going to present you how to use magnetic finite element results to set reduced order models of permanent magnet synchronous machine drives in LMS ImagineLab AMSIM. Permanent magnet synchronous machine, or PMSM, are very used in automotive applications because of their high power density and excellent efficiency. The design of such device requires finite element for a good magnetic sizing with a good geometry definition and material definition, and also system validation, for example using simulation and LMS AMSIM. Both are important, and therefore the process of reducing finite element model into system simulation model is a key step. To do that, the methodology is to use finite element results to generate the right characterization data that we can use as input parameters into LMS AMSIM. The characterization data consists in 3 sets of maps. First, flux linkages that will represent the machine magnetic saturation and the related nonlinearities. Then, the iron losses of the machine. And finally, control-related data such as torque limits and optimal carrot set points for the various operating conditions. How to obtain this data is explained in the demonstration examples of the electric motors and drives library that we can access through this path. This example explains the model reduction process, and in this first step, the right simulation to perform with the finite element tool to obtain the data in the right format for AMSIM is explained, and also scripting templates to reuse and adapt are proposed. In this second step, this data that we obtained can be post-processed to get the right control-related data, and here again, templates are proposed. Now we can use this data into a vehicle model in LMS AMSIM that features an electric powertrain with a battery, a torque control, a voltage source inverter, and a PMSM. The flux linkage and iron losses can be input as text parameters here in the parameter list of this component. It is a quasi-static component using a space phasor representation. The current dynamics are neglected for the fastest simulations. This approach is very efficient for a vehicle simulation, and I can launch a simulation here. It is very fast, and we can get the results with these saved plots here. We can observe the various losses in the system, so battery, inverter, machine electrical and mechanical losses, as well as the energy conversion from the battery to the wheel, but also machine temperature assessment or the battery current load. So with this analysis, we are able to evaluate the performance of a design, but also to identify the mechanical, electrical, or thermal constraint of each component of the system, and we can refine the individual requirements of those components. And on a second step, we can perform design of exploration to narrow down the design space of the PMSM drive. Now we can also use the data we discussed in a PMSM drive model, a reduced order model, that features the dynamic of the current. So here they are controlled in closed loop with a field-oriented vector control, and we can observe their time variation and their regulation. We can also look at the electromagnetic torque and observe how it evolves with time and how it is regulated. So this model enables to validate the performance of a control and eventually ensures a better system design. So to conclude, we showed how to use magnetic finite element results to get the right characterization data that we can use in reduced order model of permanent magnet synchronous machine drives in LMS-MSIM. This approach enables to front-load the development effort and ensures a better system design. Thank you for watching. For more information, please visit our website.